Coming back, let's continue for the morning session. It is a pleasure to have with us Andy Neitzke to talk about Abelianization and conformal blocks. Oh, am I supposed to have microphones?
Is that all right? Great. So I'd like to thank the organizers for the opportunity to come to this virtual conference. I've already learned a lot, and looking forward to the rest of the time. This talk on abelianization and conformal blocks. It's a report of some work from 2024 with Chen Yu Hao, which when it was preprinted, it appeared on HepTH, and so that'll give you some indication that this work is still kind of in the physics literature. So I will tell you about some constructions, and I'll tell you the properties that they're supposed to have, but I'm not going to be telling theorems today. And anyway, so part of it has already appeared, and then some of the work is work in progress with David Bellini and David Gayoso. So let me tell you some of the goals. So goal of the work. So first goal has to do with the Heck-Miller space. So suppose S is a surface, it's a compact surface of genus G with n marked points. Sometimes you say pinchers. I'll use those words synonymously. Then, I think as participants of this conference very well know, there's the corresponding beautiful space, Heck-Miller space for that surface. Parametrizing either complex structures or hyperbolic structures up to identity-connected diffeomorphisms. So a very nice and canonical space associated with the surface, which we like to study. It's manifold, real dimension 3G, if G and N are big enough. Real dimension 3 to minus 3 plus. If I don't fix eigenvalues of, so one other thing to say about it is that it sits inside as a component in the moduli space of in the Durham space. First, the character variety, the SL2R character variety. And then when I think of it in the character variety, I can either fix or not fix the eigenvalues of monodromy around the punctures. If I don't fix them, then it has this dimension, it's Poisson. But it has the Poisson structure has symplectic leaves. Symplectic leaves. Dimension. Oh, sorry. Double. 16 minutes. Thank you. Yeah. Right. 16 minus 6 plus 2. Thank you. Okay, so we have this nice Poisson space or family of symplectic spaces associated with the surface. And when we have a symplectic space, it's a natural question. At least as physicists, we always want to try to quantize it. So there's a question, is there some natural quantization of Heck-Miller space? Okay, so what would it mean to have a quantization? Well, on Heck-Miller space, we have a natural class of distinguished functions, which are the trace functions. So you look at the holonomial around any loop, you take the trace of the holonomial, that gives you a function on the Heck-Miller space. And those functions form a commutative algebra, so call it A. So trace functions. And part of quantization, part of the program of quantization would be to deform that to some non-commutative algebra, depending on a parameter h bar. Where it's a leading order in h bar, the commutator is controlled by the Poisson bracket. Here by quantization, I mean more than that. So this, I think people would sometimes call deformation quantization. If you just take the algebra of observables and you try to deform it to some non-commutative algebra. That's already a very interesting question. Here, by quantization, I want to ask for a little bit more. I want to ask not only for algebra of operators, but also a space on which that algebra naturally acts. So this algebra should be acting on some vector space associated with the original symplectic manifold. What can we say about that vector space? Okay, maybe one thing to say right off the bat is whatever it is, it should be infinite dimensional, because the heuristic is that the dimension of the space is like the symplectic volume of the manifold that you started. Here we're starting with a Teichmüller space, which is infinite symplectic volume. So this is going to be some infinite dimensional vector space. Some interesting infinite dimensional vector space, which we call the quantization of Teichmüller space. Okay, so how do we think about this question? Well, there's many approaches, but there's at least two kind of important approaches to this question. So one approach to this is what I'll call cluster quantization. Oh yeah, and for most of the talk, not for everything, but often I'll assume that n is bigger than 0, and certainly here I have to assume n is bigger than 0. So this is a thing which we don't really know how to do for an unpunctured surface. But as soon as you have punctures, you can talk about it. And the idea is that you equip your surface with a little extra structure. You equip it with an ideal triangulation. So pick an ideal triangulation of the surface. Once you pick an ideal triangulation, you get a distinguished coordinate system on the Teichmüller space, which is the shear coordinates. So not only a coordinate system, but a Darboux coordinate system. So it's a coordinate system in which the Poisson brackets take a very simple form. Once you've done that, what you essentially do is you identify this kind of complicated nonlinear symplectic manifold that you wanted to quantize. You identify it after making a choice. You identify it with just a linear space, a symplectic linear space.
So S is both the surface and the symplectic space?
I thought I used S only for the surface. I meant to use S only for the surface, and T of S for the T of S for Teichmüller space, and I didn't introduce a name for the symplectic leaves expression. Yes, we get a coordinate system on Teichmüller space, the shear coordinates, and so that identifies. You could think that that identifies T of S with a linear symplectic vector space. With the vector space with a skew parent. That's a simple example of a symplectic manifold, and that's one that we do know how to quantize, preserving at least all the linear symmetries. So you can quantize that. So in one sense, quantizing a symplectic vector space, and what you would get then is you have a symplectic vector space of dimension, r to of dimension 2m, that its quantization you identify with just L2 functions in m variables. So in this case, it'll be L2 functions on, okay, half this. So that's an even number. Okay, so 3g times 3 plus that. So that's one approach to quantization, is to say, okay, I have this coordinate system, and I'll just do the most naive possible linear quantization in that coordinate system.
How do you choose polarization?
Yeah, okay, good. You have to choose the polarization. So strictly speaking, I choose an ideal triangulation, and I also choose a polarization. But if you choose some other polarization, then it just changes by Fourier transforms. Is usual. Global coordinates, yeah, on Teichmüller space, yeah. I'm not talking about so yeah. These coordinate systems, if you think of the complex character variety, of course, they would be, they live only on some open dense subset. But now I'm talking about just doing it on Teichmüller space. So that might, for a second, sound like an answer, but then you realize this answer is not really satisfactory because it depended on the choice of the triangulation. And I want something that will be invariant under all the natural symmetries. In particular, I certainly want something which will carry a representation of the mapping class group. So mapping class group X acts on type Miller space, and you want it to also act on the quantization. That's one of the important things. So at first, this looks a little bad because it depends on a triangulation. But then, so this is, I should give an intro. So this is, I think, first done by Kavli, and later sort of extensively generalized by Goncharov in the kind of general cluster context. So this, so it seems to depend on the choice of triangulation. But what Chekhov and Goncharov showed is that if you have two triangulations that differ by a flip, there's actually a canonical isomorphism between the corresponding spaces, which kind of intertwines these intertwines with quantization. There are natural intertwines. If I have two ideal triangulations, maybe one of them looks like this. I'm just drawing part of the triangulation. I take this triangulation and this triangulation. Each of these triangulations, I associate one of these quantization vector spaces. And then there's a canonical isomorphism between these two that kind of implements the effect of this flip. It's written, if you want to write it concretely, it's written in terms of the quantum dilogarithm operator. So using that, you get rid of the dependence on the triangulation. You have a whole bunch of vector spaces, but you also have canonical isomorphisms between them. And so ultimately that gives a version of the quantization. So that's one thing you can do. Now, that answer, okay, for some purposes, that answer is satisfactory. I mean, if you just want to construct a representation of the mapping class group, you live with the fact that it depends on stuff. It's okay. But there was a very different answer to this question coming from physics. So this was answer 1, and now let me tell you answer 2. Two has a completely different flavor, and it comes from conformal field theory. So it's, I think it was first written down, this idea was first written down by Berlinde, who developed much more by Jörg Teschner and many others. And there the statement is, the vector space that we're trying to make, we don't make it by this kind of algebraic combinatorial game here. Instead, we just say what it is, and what it is supposed to be the space of Virasoro conformal blocks. I have to tell you what this is, of course, but the name of it is the space of Virasoro conformal blocks at central charge. I tell you what this is, but it's just some number, and here's the formula for the number. Okay, so this is defined in some totally different way. It's kind of an analytic thing, has to do with geometry of Riemann surfaces. We'll say what it is in a little bit. But now I can say that the first kind of goal of this work is to explain why these two answers have anything to do with each other. So the question is, so this is still my goal 1. Is to explain why these two quantizations of type Miller space have anything to do with each other. And so I'll describe for you a construction which is meant to explain that. So far, unfortunately, only for one value of h bar. So far, we answered the question only when h bar, the quantization parameter, is equal to 1, very special value. We'll see why. So that corresponds to, in the language of Virasoro, it corresponds to the Virasoro central charge will be equal to. Okay, so that's one goal. Let me say a couple of other goals. So the second goal, but it comes almost as a kind of byproduct of trying to answer the first question. So the construction I tell you is going to lead to some new formulas. So it'll give new formulas for various kind of objects that are interesting in mathematical physics. So for example, for isomonodermy tau functions, matrix model partition functions, and then closely related to that, topological string. Okay, so hopefully I'll be able to at least show you one of those formulas. So as I say, all these formulas, emphasize, all these formulas are conjectural formulas, but you produce a whole system of new formulas. And then the third goal, so certainly in this talk, I'll only talk about the situation of SL2, the ordinary type-Miller space. But part of the idea is that the machine that we use is a machine which kind of has a natural SLN version. And so the hope would be to also talk about SLN, so the higher type-Miller spaces, quantization of higher type-Miller spaces, also relate them to something in the conformal field. Okay, so those are the goals. And let me also say what the kind of basic strategy is going to be. So the basic strategy. And the basic strategy is something that I think will be very familiar at a Higgs bundle conference. So the basic strategy is going to be, we're trying to study something on a Riemann surface, C, and the thing we're trying to study has something to do with SL2. It's quantization of the SL2 type-Miller space has something to do with SL2. And the idea is going to be that this problem is hard, but we're going to relate it to something simpler that lives on a branch double cover. And that branch double cover, in fact, will be like a Hitchin spectral curve. So it'll be something which could have been the spectral curve of a Higgs bundle. Although we won't use the Higgs bundle too explicitly today. And so the idea is that here I do something that has to do with GL1, right? Like the relation of a Higgs bundle, rank 2 Higgs bundle here to a rank 1 Higgs bundle here. Or like the relation between an SL2 flat connection here and a GL1 flat connection here, which is a little subtler. So we're going to here, SL2, this is going to have to do with Virasoro conformal blocks. These are the objects which we want to construct. And we'll relate them to something that has to do with GL1, something easier called Heisenberg conformal. So that'll be the game. Okay. So, one other thing I should say. So, I'm saying there's a relation between GL1 and SL2. Actually, what we'll get most directly is, rather than GL2, what we'll really get is, that's right, rather than SL2, what we'll see most easily is GL2. And so I'll mostly suppress that difference between SL2 and GL2.
This is why C equals simple charge is long.
Instead of 2?
This is why, because you're relating
in a sense, yes, but I'd say not really, actually. We'll see where this equals 1 comes a little later. You could relate it to Heisenberg and other central charge. There's just an obstacle. But I think that obstacle will be overcome even just using Heisenberg. Okay, so I should define at least something, right? So let me tell you what a Virasoro conformal block is. So okay, so we have to fix some data. Well, not too much data. So we fix a number, a complex number, as it'll be 1 later, but for the definition, it could be anything. And we fix a Riemann surface. So up till now, I just had a topological surface, but now it really has to be a Riemann surface. So maybe it's like this. Maybe punctures. For now, let's do the puncture section. So then, from this data, there's a vector space, which I'll call it like this: the space of conformal blocks. Versor conformal blocks. So I have to tell you what's an element in this vector space. So, I don't want to ignore this. Complex vector space. So, okay, so what's an element in this vector space? What it means is a bunch of functions on the Riemann surface. So I'll write them like this. What this is, we're called correlation functions. So as far as notation, so there'll be a bunch of functions, one function for every k. There'll be a function depending on k points of the surface. So you can write a fk of t1 up to tk. But actually, the physicist notation for it, which turns out to be a good notation, is this: they write angle brackets, and then they write t of p1 up to t of p. Okay. I'll put a sign here just to keep track of which conformal block I'm looking at. So the picture is that on my surface, I'm considering a function of a bunch of points, maybe p1, p2, p3, and I think that there's some, in quantum field theory, there's some field, the stress energy tensor, and I'm computing correlations of the stress energy tensor at these points. But okay, it's just a function of these points. It has to have various properties. So what are the properties that it has to have? So first of all, it should be invariant under the symmetric group, so it doesn't matter in which order I write these things. It should be meromorphic in the PIs. So we're writing down some meromorphic functions of a bunch of points. It should have, in fact, it's holomorphic away from the places where two PIs collide. Holomorphic away from the diagonals. And the singularities at PI equals 2K, they're of some very controlled point. So to be precise, we're going to have a fourth order pole when PI approaches PJ with some specific shape. So what's called the operator product extension. So write it like this. So I'll first write it in a slightly schematic form, and then I'll explain what it means. So the idea is when I have two of these T's and I bring them close together, I'm allowed to replace it by the following. By a fourth order pole. So I have some local coordinate z, and so in that local coordinate, I have a fourth order pole with coefficient 1/2 of the central charge, and then I have some subleading stuff, which I'll write this correct: c of p over c of p minus c of q squared plus the derivative with respect to z divided by c of q plus random. The idea is we're completely fixing the polar part of this meromorphic function. Now, what does it actually mean? I'm writing this relation, but the t's, as I defined it here, they only had a meaning inside the angle bracket. So what this means is that you're allowed to insert this relation inside the angle bracket. So for example, suppose I would look at the 3-point correlator T of P, T of Q, T of R, and I look at what happens when P approaches Q. Then the statement is, the leading singularity I get by taking 1/2 C over C of P minus C of Q to the fourth. So I'm replacing the T of P, T of Q by this. I still have the T of R, and so this will be multiplied by the 1-point function T of R. And then the next term we'll have, here I've replaced the two of them by a single T of P. So I'll have T of P, and then I still have T of R, and so on. So the concrete meaning of this operator product expansion is that you kind of insert it inside the correlation functions to understand what the singularities are. And so what it means is, for example, here's the 3-point function. Its singularities are determined by the 1-point and 2-point functions. And so you have this kind of hierarchy of functions where each one has singularities that are determined by the earlier ones.
The marking depends on choice of local coordinates.
Okay. Yes. Okay. So I purposely didn't say that at first, but now's the time when I have to say it. So, so indeed, so far I said that they're just meromorphic functions, but that's a little bit of a lie. They depend on a local coordinate around each puncture, and so around each of these points. And so to finish things, I have to tell you how they depend on the local coordinate. So let's write that. So I said functions, but they're not actually global functions. They become functions only after you choose local coordinates around each of the points. And the global statement is that the coordinate transformation law is, so now, just for a minute, let me write explicitly the dependence on, so we'll have two local coordinates, I'll call them W and Z. And so the T of P in the local coordinate W can be related to the T of P in the local coordinate Z in this way. So there's a factor, dz by dw squared. Okay, plus something else. If it was just this, you would say to me, well, you should have just said it's globally a quadratic differential, right? This would be another way of saying that secretly the global object is a meromorphic quadratic differential. The thing is, it's not quite that. It's a slightly more complicated thing. So there's another term which involves the Schwarzian derivative of the change of coordinates. So this is the Schwarzian derivative. Okay, luckily I didn't write the formula for Schwarzian derivative in my notes, and therefore I can't write it here. Maybe the only thing to say is, this is some finite polynomial in derivatives of z with respect to w. The crucial thing about it is that it's 0 for Mobius transformations. And so sometimes this is useful. If you fix an atlas of coordinate charts that only differ by Mobius transformations, then you're allowed to forget about this. But then it depends on that choice. Okay, so now I completely told you what a conformal block is. Put the size here. I told you what a Virasoro conformal block is. So the claim is that the correct quantization of type Miller space should be the space of these Virasoro conformal blocks. Yeah.
Should we think conformal block as a section depends on the modular parameter of touch Miller space?
Okay, so far I'm working just at a fixed Riemann surface. And I think you're asking me, suppose I now change the Riemann surface, what happens? So you could say that there's a bundle. So over like MG, there's a bundle whose fiber is the space of conformal blocks at a point, and there's a connection in that bundle. There's a twisted connection because of this Schwarzian derivative stuff. Roughly speaking, there's a flat connection in the bundle.
And also, there's some axioms in this conformal block should satisfy word identity.
I mean, what I'm writing here is essentially the word identity. So what I'm writing here is not the most usual definition of conformal block, but it's the one that's kind of it's the one that I think is best adapted to describe anything in finite time. I don't have to say what a vertex algebra is. Okay. So now the basic question. is, particularly if we want to prove this statement about identifying different quantizations, we're going to need some machine for actually producing such objects. And a little bit of experimentation will convince you it's not that easy to just write them down, kind of to try to guess the functions. So I'm going to describe kind of a new analytic scheme for producing these objects. Okay. Oh, but I guess I should at least say in words that this is a very well-studied subject. So a lot of people have given constructions of conformal blocks. In particular, recently there's been this spectacular progress in probability theory, where people have given a totally rigorous construction of the Liouville conformal field theory. And that gives a very nice construction of these things when the central charge C is greater than 25. Here we want to do central charge equals 1. Okay, still there's a lot of work out there. The construction I'm going to tell you is somehow different and adapted to the thing I want to do. Okay. So we have done it particularly like if you're looking for review articles by Jürgen Teschner will explain a lot of what's known about these gross probabilities. Okay, so but the construction I want to describe is by this procedure of Abelianization. So again, I'm going to have this branch double cover, spectral curve. And I'm going to pick, just like we did when we talked about the quantization, I'm going to pick a polarization, meaning I'll pick A and B cycles on C twiddle, like a symplectic marking of H1 of C twiddle. And then I'm going to pick, then in that quantization, I'm going to pick a kind of delta function state, which means I'm going to pick a number, right? A tuple of numbers up to the genus of this curve. Real numbers, actually pure imaginary numbers. Okay. And now, given this data, we're going to construct a conformal block down here. So okay. So really, I'll only be able to give the sort of most important features of this construction. So what we're going to do, we're going to relate them to something simpler up here. What's the simpler thing? The simpler thing is going to be conformal blocks for the Heisenberg algebra. So I start again. Now, instead of Beer, I write Highs. Means again a system of correlation functions. Now I write them. Before I wrote T, that was the stress tensor. Now we'll use a different symbol J, which is like a free boson. Anyway, get some. You can think of just some formal symbol. Now these points are going to be points of the cover. The idea is we're going to relate correlation functions here to correlation functions here. So we're going to have functions on the cover obeying all properties the same as before, except for the shape of the singularity. So let's write the shape of the singularity. So now it'll be J of T, J of Q is much simpler, just a second order poles. The coefficient of 1. And that's all, no residue. Okay, so we just ask for things with a second order pole when the points collide. And then the coordinate transformation law will be that of a holomorphic differential. Just dw by dz, no Schwarzian derivative, nothing complicated. So this is a much simpler thing. And here, if you try to make functions with this property, a system of functions with these properties, you find that you can do it using just kind of, analytic geometry of Riemann surfaces. So let me write the first couple correlation functions. So I'm going to write an element psi twiddle A in the space of Heisenberg blocks from the cover. And here, we can make a totally explicit formula. The explicit formula is like this. So for the 0-point function, I'll just make it 1. For the 1-point function, if you think about what it has to be, the 1-point function, according to everything we said, has to be a holomorphic 1 form on the surface. It'll be a holomorphic 1 form. So the holomorphic 1 form with the property that its integrals over the A cycles are the numbers we showed. So we had these numbers that we fixed, and we'll use them as the periods of a holomorphic 1. And then the higher correlation functions. So I'll just write the 2-point function. The 2-point function will be eta of p times beta of q, plus now I have to put something as a singularity when p approaches q. But there's a canonical such thing with this second order pole. There's something called the Bergman kernel. And that's an object which is a globally defined object on the Riemann surface. It's kind of it's like a holomorphic differential in each variable. And it has exactly this property that it has a second order pole like this when the 2 points collide. And then in a similar way, you can write formulas for all the higher point functions. So this problem, the problem of writing correlations of you can say correlations for the free boson roughly. This problem you can do it explicitly. Okay, and now my problem is to get from the correlation functions on the cover, solving the simple problem, GL1 problem, to the correlation functions on the base, solving the GL2 problem. Okay. So the first thing you try is a kind of naive push forward. In the same way that if you had a flat connection on the cover, if you had like a flat GL1 connection on the cover, and you wanted to make it a GL2 connection on the base, the first naive thing you might try is just to push forward the connection from the cover to the base. That doesn't work. We know it doesn't work because there's monodromy around the branch points. For Higgs bundles, it works. For flat connections, it doesn't work. But then there's a way to fix it. And we're going to do the parallel thing here, not for connections, but for this kind of quantized connections. So let me tell you first what the naive push forward is, and then what the ingredient that fixes it, and then I think I'll be out of time. So first I kind of naive push forward of conformal blocks. So that would be the following. I have my double cover. I have my surface downstairs, and I want to compute correlation functions of, say, correlation functions involving points of the base. And so the simplest thing I can imagine doing is I'll just lift those points directly to the cover. So it's 2 lifts. I'll call them Q1 and Q2. Here's Q. Lift it to Q1 and Q2. And then we try lifting the correlation functions like this. I could say, well, every time I see T and P on the base, I'm going to replace it by some combination of things inserted on the cover. And there's a natural guess that's kind of motivated by things that were done before in physics, which is the following. You put the J at P1, put the J at P2, take their difference, and then you square it. Well, if you square it, you'll have a singularity because you'll have J of P1 times J of P1. You don't want that, so you do so-called normal order. You expand the local coordinates around the point and you throw away the singular term. Then that's a canonically defined thing. And then you would try to say, okay, the correlation function of, say, T of P, T of Q. So the proposed construction of these functions could be to just do the following. You do this Abelianization of them. And now you compute the correlation function on the cover just using, the ingredients we said there, homomorphic one forms and Bergman kernels and so on. That's a candidate formula, and you can ask, okay, does it have the properties that it's supposed to have? Well, okay. The answer is no, but let's see why not. So it almost works. In particular, it has the correct singularity. As, for example, the point P approaches Q. More generally, if I have 10 insertions and 2 of them collide, I get the expected singular behavior as the 2 points approach each other. With coefficient turns out to be exactly C equals 1 then. So that looks good. I mean, it's meromorphic and it has the singularity it's supposed to have. It also has the right coordinate transformation law, actually, that complicated Schwarzian derivative somehow comes out just from this prescription. The only thing that's not good is the prescription, as I told it to you, it really relies on not being at a branch point. So the problem is the same problem that you have for push forward of flat connections, which is something goes wrong. Oh, can I be seen over here? Yeah. The problem is that the correlation functions which you compute in this way, there's no guarantee that they will behave well when the position of the insertion approaches the branch point. And it turns out that sure enough, they don't. An unwanted singularity as P approaches each branch point. So I have 2 minutes, right?
Yes.
Yes, okay. So we need to somehow cure this singularity, and that's where the sort of new ingredient in this story comes from. That's where you need a new ingredient. So I'll just write for you what the new ingredient is. So to show the singularity, we introduce actually the same gadget that you needed for the story of flat connections. You introduced a spectral network. But pragmatically, we're talking about SL2. What a spectral network means is just emerging from every one of these branch points, we draw a kind of tripod, 3 lines like this, that start at the branch point and end up at the punctures. So we'll have a picture like this. This data, combinatorially wise, this is the same data as giving an ideal triangulation of the punctured surface. So I said at the beginning, we're trying to relate conformal blocks to this cluster quantization, which uses ideal triangulations. So here's the moment where you use an ideal triangulation. You have to draw this picture. All right, I just write the formula. So the problem will be cured by adding some iterated integrals over this spectral network, which I call W. And so the iterated integral that you have to do is given by a slightly complicated formula. Let's see. Yeah, maybe I think I don't quite have time to do justice to the formula. So I'll just tell you that the key ingredient is some iterated integrals that are built completely out of the Heisenberg correlation functions, but in order to write them down, you use the data of this spectral network. So ultimately, the kind of formulas that you get for the correlation function, they involve determinants of integral operators, where the integral operator is defined on the lines of this spectral network. And so it's a new kind of slightly complicated looking formula, but it's explicit formula. And then you can go and verify its properties, which is what we're now doing. Anyway, good. I think I better stop there. So thanks very much.
So questions? Is this new operator in the vertex algebra?
It's like an integral of things that are in the vertex algebra. Okay, so now I get it. It's the exponential of 1 over 2 pi I times the integral over W of, take the two lifts of a point. Yeah, I should just read it. So integral over PMW, you lift it to the two sheets of the spectral cover, and you insert psi plus and psi minus. Now, psi plus and psi minus they're not directly in the vertex algebra, but they're themselves built from integrals of J. So this is like the boson-fermion correspondence. So yeah, we can write a formula for that. So psi plus of P, psi minus of Q is like the exponential of the integral from P to Q of J. Normal one. So ultimately, the whole thing is built out of J, but in a complicated way, which involves iterated integrals and sort of two exponentials and so on. Yeah.
Can you say a few words about the relation to cluster quantization?
Right. So here what I was doing is I was proposing a construction of an element in the space of conformal blocks for every, my data A there, which was A1 up to A G twiddle. Now, those elements you should think of as being, in the cluster quantization, you identified the quantization with just functions of G twiddle variables. The number that appeared there, 3G minus 3 plus N, is also the genus of it's almost the genus of the spectral cover. Not for the difference between GL2 and SL2, it would have been the genus of the spectral cover. So here we have a bunch of variables. A number of them is the genus of the spectral cover. And we're producing elements of this conformal block quantization. Those elements you should think of as corresponding to the kind of delta functions in the L2 quantization. So they're not literally vectors in L2, but they're kind of distributional elements of that vector space. So that's the way the map is supposed to go. And you construct the action of the algebra of operators on both sides, and you check that they match and so on.
This might point at a very question, but how do you quantize the time aspect by using spectral network? Since its spectral network only lives on the only curves, so you vary it, or how does this give a?
I mean, here we hold the Riemann surface fixed. You hold the Riemann surface fixed, and you construct a vector space corresponding to that fixed Riemann surface. But then there's a connection that allows you to vary the Riemann surface.
That is a way to quantize the space.
Yeah, but let me emphasize, I mean, the idea is that you pick a single point of Teichmuller space, and you produce a vector space depending just using the data of that single point. That is already the quantization of Teichmuller space. Then there's a separate fact, which is that it doesn't depend on the base point.
I have a question. So you have different symplectic leaves corresponding to different holonomic, compact, unipotent, whatever, minus unipotent. Where is the dependence on the holonomic?
Okay, good. So we can talk about it. So when I gave you the definition of conformal blocks, I gave you the definition. I actually gave you the definition without functions. So for the function surface, there's an additional thing, which is the correlation functions also have singularities when you approach the punctures. And then it's a second order pole, and the coefficient of that second order pole is controlled by the hole.
Another question there.
So, when you do say not equal to 1,
Okay, if you want to do C not equals to 1, okay, so I think it's a beautiful question. I'm sure that there's a solution to this, but there is a clear problem, which is for C not equal to 1, the formula you would try to write, the most obvious formula to write coming from things in the physics literature would be the following. You would write J of P1 minus J of P2 squared. This is the thing I wrote before. This would give you C equals 1. There's another term which you would like to write, which is some coefficient, the derivative of J of P1 minus J of P2. This one would have the correct operator product if Q is, H bar plus 1 over H bar. So this looks great. The problem with it is this one didn't depend on what I called P1 and what I called P2 because this is odd under the interchange and then I square it. So it didn't depend on that choice. This one is odd under the interchange. So this one makes sense on a trivial double cover, but as it sits, it doesn't make sense on a branch double cover. It's not hopeless. It should be possible to deal with this. So there's some idea, but it's not. But there's a clear obstacle. That's the obstacle.
So this expression follows from Sugawara construction.
Right. What I'm writing here is the Sugawara with a background charge. I think just this would be Sugawara usually. Yeah.
No further questions. Let's thank Andy again.
What's on the
Yeah.